Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started.
You might think flying a drone is all about mastering the sticks.
Yeah, getting those smooth shots.
Exactly. Nailing that perfect cinematic sweep or, holding position like a statue. But beneath the surface, inside that aircraft you're controlling, there's this incredible, complex web of onboard systems, constantly working, calculating, sensing, reacting, just to keep it stable, safe, and exactly where it's supposed to be. Understanding these systems, not just that they exist, but how they work, where they can fail, and, importantly, what the regulations demand of you as the pilot, is absolutely critical, especially as we move into more advanced operations, things governed by, say, the Canadian aviation regulations, the CARs for RPAS.
Right, remotely piloted aircraft systems. And you often need that SFOC, the Special Flight Operations Certificate, for the complex stuff.
Exactly.
And it's true, it's the hidden architecture of safe flight. And with regulations evolving, particularly in Canada, understanding these core systems isn't just, good practice anymore. It's a fundamental requirement for competent operation. It's explicitly tested in places like Transport Canada's knowledge requirements for Advanced RPAS, TP 15263.
So for this deep dive, we've pulled together a stack of sources covering the real essentials you need to know about what's inside that drone. We're talking about the drone's sense of place and stability, that's navigation and flight control.
Yep.
Its lifeline back to you, the pilot, command and control, or C2.
Crucial.
How it perceives threats in the sky, detect and avoid, DAA, the whole concept of backup systems to prevent catastrophe, redundancy, and the fundamental physics of payload and balance.
Our mission here is to really unpack these technical topics in detail. We want to clarify some crucial distinctions that maybe aren't immediately obvious, like the difference between DAA and just basic obstacle avoidance.
That's a big one.
It is. We need to understand what regulatory bodies like Transport Canada explicitly expect from operators regarding the performance and monitoring of these systems, especially with recent regulatory changes. And ultimately, we want to give you the in-depth insights you need to be genuinely well-informed, confident, and safe when operating an RPAS, particularly in scenarios that push beyond basic visual line of sight, or VLOS, operations towards things like flying beyond visual line of sight, BVLOS.
And trust us, even in these technical details, there are some genuinely surprising nuggets and aha moments hidden in plain sight, like how some of the displays you see on drone controller screens actually borrowed ideas from classic video games.
Oh, yeah. That's interesting. Or why studying bird vision is actually influencing cutting-edge drone tech development. It's pretty cool stuff.
It really is.
It's about getting that shortcut, that deep understanding of what's really happening inside the aircraft you're flying, interacting with, or maybe planning complex missions for. It's the knowledge that truly separates, a basic stick pusher from a truly competent RPAS operator. Let's get into it.
All right. First up, let's look at the core intelligence, the brain, and its senses. Navigation and flight control. This is fundamentally about how the drone knows where it is, what direction it's facing, and, how it stays stable in the air.
Okay. So at the very heart of any modern drone is the flight controller, or FC. You can think of this as the aircraft's central processing unit, its autopilot computer, all rolled into one. It's a complex piece of hardware and software.
The brain, basically.
Exactly, the brain. Its primary job is to take all the incoming data from you, the pilot, through your commands, and from a whole suite of onboard sensors interpreted in real time, and then translate that into precise commands for the motors or, in fixed-wing systems, the control surfaces like ailerons and elevators, all to keep the drone stable, execute the desired maneuvers, and follow navigation instructions.
So the FAC is constantly crunching numbers based on what it's receiving from the outside world and from inside itself.
Precisely. And it's not just looking at one data stream in isolation. Our sources talk about something called sensor fusion, and this is a really fundamental concept for drone reliability. What's happening there is that the FEC doesn't rely on just one type of sensor for critical functions, like knowing its position or orientation. It's constantly combining data from multiple, often very different inputs simultaneously.
Like a cross-check system to make sure everything agrees.
Exactly. It fuses data from the Global Navigation Satellite System, that's GNSS, which includes systems like GPS, the US one, Galileo from Europe, GLONASS from Russia, Beidou from China for global positioning.
Right.
It combines this with the data from the Inertial Measurement Unit, or IMU, which uses accelerometers and gyroscope to measure things like orientation, pitch, roll, yaw, and acceleration. It uses data from the compass or magnetometer for heading and from the barometer for relative altitude pressure. And at low altitudes, many drones also use a visual positioning system, or VPS, with downward-facing cameras to track movement relative to the ground.
Wow, that sounds robust, combining all those different inputs.
It is, because the idea is that by intelligently combining these diverse inputs, a process often involving complex Kalman filters or similar algorithms, the system gets a far more accurate, more reliable, and more stable picture of the drone's state and position than any single sensor could provide on its own.
Makes sense.
And crucially, this also means if one sensor's data degrades, maybe due to interference or a partial failure, the FC can often identify the unreliable data and continue to maintain stable flight, possibly with slightly reduced accuracy or maybe a change in flight mode, using the reliable data from the others. It's a foundational layer of internal resilience.
Okay, let's zero in on GPS, or more broadly, GNSS. This is what gives the drone its sense of absolute place in the world, its latitude, longitude, sometimes altitude. It's absolutely essential for automated features like position hold, the automatic return to home feature, RTH.
Yep, RTH.
Setting up virtual boundaries, geofences, and flying pre-programmed waypoints in autonomous missions. But the sources are very clear that GNSS isn't foolproof. It's described as having a dynamic nature. What does that mean in practice for you, the pilot? Is just getting a GPS lock enough?
This is perhaps the most critical point many new operators misunderstand, and it's a common scenario tested on advanced exams. GPS lock, good positioning. You can have a solid-looking GPS lock with enough satellites showing on your screen, maybe 10 or 12.
Yeah, looks good on the display.
Right. But the quality of that calculated position, how accurate and reliable it is, can and does change during the flight. It's dynamic. Why? Because the quality of the signal and the resulting accuracy depend heavily on the instantaneous geometry of the satellites your drone is receiving signals from relative to your location. If the satellites are all clustered together in one part of the sky, the geometry is poor and the calculated position is less accurate, even if you have many signals.
So it's not just quantity, like how many satellites you see, but the arrangement of those satellites in the sky that matters for accuracy.
Exactly right. That's precisely where metrics like HDOP, horizontal dilution of precision, come in. A lower HDOP number indicates better satellite geometry and thus better horizontal positional accuracy. PDOP, positional dilution of precision, includes the vertical dimension too.
Okay.
The sources strongly stress that for any critical operations, especially where precise position is required, you absolutely must be monitoring the satellite count and the HDOP, DOP values continuously in flight, not just doing a quick check before you launch. They suggest aiming for a minimum of, say, 10, 12 satellites and an HDOP generally below 1.5 or maybe 2.0 for really stable, reliable position hold and navigation. If those numbers start getting worse mid-flight, that's your warning sign. That's the system telling you something's degrading.
And what causes this quality degradation? What specific scenarios should a pilot be acutely aware of where GNSS might become unreliable mid-flight?
Oh, plenty of things. Multipath errors are very common, especially in urban areas, near large bodies of water or reflective surfaces like metal roofs or even wet pavement.
Multipath, like the signal bouncing around.
Exactly. The signal doesn't just come directly from the satellite, it bounces off one or more surfaces, buildings, the water, metal, before reaching the drone's receiver. The receiver then gets multiple copies of the same signal, slightly delayed, which fools it into thinking the drone is in a slightly different location than it actually is. This causes position drift, or sometimes even sudden jumps in reported position. Then there's electromagnetic interference, EMI, or radio frequency interference, RFI, high voltage power lines, cell towers, radar emitters like those found on large port cranes or ships' industrial equipment. Even other strong Wi-Fi signals can emit radio noise that corrupts or just drowns out the very weak GNSS signals.
And that affects the compass too, right?
Often, yes. That same interference can also mess with the compass. This can lead to signal loss entirely, severe position drift, or erratic yaw movements because the compass is getting confused. Flying directly underneath or very close to major power infrastructure is a classic way to lose GNSS and compass reliability simultaneously. It's a double whammy. Physical obstructions are also a factor. Flying in urban canyons between tall buildings or over dense tree canopies can simply block signals from many satellites, reducing the satellite count and worsening the geometry, which means higher HDOP.
So fewer signals getting through.
Right. Heavy rain or even thick cloud cover can slightly degrade signal quality too, though usually not severely enough to cause total loss unless other factors are present. And temporary space weather events like strong solar storms can impact the ionosphere, which the signals pass through, causing temporary disruption globally. Though honestly, that's less common than local interference from buildings or power lines.
Wow, so it's not just about being outdoors with a clear view of the sky. The environment around you matters intensely, even things on the ground.
Absolutely. And this is where the Visual Positioning System, or VPS, comes in, but primarily at low altitudes. VPS uses downward-facing optical or sometimes ultrasonic sensors to detect features on the ground and measure the drone's movement relative to those features. It's fantastic for maintaining position and altitude stability when very close to the ground or indoors where GNSS is unavailable.
Useful for landing or close work.
Exactly. However, it's not a replacement for GNSS at altitude and can be unreliable over featureless surfaces like calm water or sand, or if the ground itself is moving, like if you're operating from a boat. Some experienced professional operators might even disable VPS outdoors at altitude if they have reliable GNSS, as certain ground textures or slopes can occasionally cause minor altitude oscillations or instability if the VPS data isn't perfectly integrated by the flight controller. It's another example of really needing to know your drone and its specific sensor quirks.
So the responsibility falls squarely on the pilot to not just check for a GNSS lock before takeoff, but to monitor its quality continuously during the flight. What should they do if they see that GNSS quality is degrading significantly mid-flight? Say HDOP starts climbing.
Yeah, the sources say you must monitor GPS accuracy in real time and respond to deterioration. This isn't optional, it's a critical pilot action for safety. The appropriate response depends on the severity and the operational context. If you see the satellite count dropping below recommended levels, say below 10, or the HDOP increasing significantly, maybe getting above 2.0, especially if you're operating near hazards or relying on precise position hold.
Like for inspection or mapping.
Exactly. You need to be ready to switch to a manual control mode that doesn't rely on GNSS position, like ATT mode. If the degradation is severe and rapid, or you're in a critical area like near obstacles or people, the correct action is often to terminate the mission and land immediately under manual control. The pilot needs to have the skills to make that judgment call and execute the fallback procedure based on the real-time data on their ground station display and their knowledge of the environment.
Let's talk more about that fallback mode, ATT mode. What exactly is happening when the drone switches to ATI? What does the pilot need to be ready for?
Okay, in most consumer and many professional systems, when the GNSS position signal becomes unreliable or is lost entirely, the flight controller will automatically switch to ATI mode. ATTI stands for attitude mode. The key characteristic is that the APC will continue to use data from the IMU and barometer to maintain the drone's orientation, its pitch, roll, and yaw attitude relative to the horizon, and its altitude relative to the takeoff point using the barometer.
So it stays level and holds altitude.
Barometric altitude, yeah. But, and this is the crucial part, there is no position hold, no altitude hold relative to the ground based on GPS. Because it's no longer receiving reliable position data from GNSS, the drone will simply maintain its attitude and barometric altitude, but will start drifting with the wind like a kite.
Ah, okay, so if there's any wind, it's just going to get pushed.
Exactly. If there's no wind, it might stay relatively still horizontally, but even small gusts will push it around. Which means if you're flying near obstacles or trying to hold a specific location, you have to be able to manually counteract that drift with the sticks.
Which brings us back to pilot skill.
Absolutely. Transport Canada expects pilots to competently handle ATI mode, flying clear of obstacles and landing manually in the event of a GNSS failure. This is why possessing strong manual stick skills isn't just for fancy flying, it's a fundamental safety requirement for handling system failures gracefully. Our sources point out that you could legally fly advanced ops with no GPS if the FC Plus pilot can control flight safely. This means understanding the limitations of ATI mode and having the manual proficiency to safely fly the drone back and land it while it's drifting.
So it's not just knowing how to fly with GPS, but knowing how to fly without it when the system requires it. That makes sense.
Precisely. And this is where know your drone becomes paramount again. Different platforms behave differently in various failure scenarios. Some might automatically attempt an auto land immediately upon losing GPS. Some might go into a stable hover if they have sufficient alternative sensor data beyond GNSS, like strong optical flow or LiDAR. Many fall back to ATI. Advanced pilots don't just know the normal flight modes. They know all failure behaviors for their specific aircraft model and payload configuration, and they practice handling them.
Like what happens if it loses one battery, or the compass fails, or the C2 link is intermittent.
Exactly. Understanding the specific behaviors allows for faster, safer responses during emergencies. It's about anticipating what the machine will do when things go wrong.
Okay, before we move on from navigation, let's quickly touch on the other key sensors involved.
Yeah.
The IMU and the compass. We mentioned they are fused with GNSS data, but what are their specific roles and vulnerabilities?
Sure. The IMU, or Inertial Measurement Unit, is absolutely fundamental for split-second stability. It's a small, often cube-like component packed with microelectromechanical systems, MEMS, like accelerometers and gyroscopes. It constantly measures the drone's angular velocity and linear acceleration in all three axes.
Tiny little sensors measuring movement.
Yeah, very precisely. From this data, the flight controller calculates the drone's current orientation, its pitch, nose up down, roll, wing up down, and nose left right. It's vital for keeping the drone level and stable moment to moment, processing data thousands of times per second. While IMU data can experience drift over time, think of it like a tiny error that accumulates. The GNSS and compass data are typically used to correct this bias periodically to keep it accurate over the long term.
And the compass.
Yeah.
That seems straightforward, just telling it which way is north.
Well, yes and no. The compass, or magnetometer, gives the drone its magnetic heading. This is essential for stable flight, particularly for accurate yaw control and flying straight-line paths, like for mapping missions. The flight controller uses the drone's GNSS location to reference a built-in or real-time magnetic model and calculate the local magnetic declination. That's the difference between true north, the geographic pole, and magnetic north, where a compass points. This difference varies significantly depending on where you are on Earth.
Ah, okay. So it needs the GPS location to figure out true north from magnetic north.
Correct. It then uses this to provide a true heading reference for navigation. But, like GNSS, the compass is very vulnerable to interference.
Right. You mentioned that earlier with power lines.
Very much so, perhaps even more so than GNSS in certain environments. The most common sources are ferromagnetic materials, basically, metals that can be magnetized, and sources of electromagnetic fields. Think large steel structures, steel buildings, bridges, transmission towers, railroad tracks, even large vehicles or metal fences.
Lots of metal around infrastructure.
Exactly. High voltage power lines generate strong electromagnetic fields. Industrial equipment, even large electric motors or transformers, can create local magnetic anomalies. This interference corrupts the magnetometer data, confusing the drone about its heading. The symptoms are classic: unstable heading, drifting yaw, difficulty flying a straight line, and the dreaded toilet bowl.
The toilet bowl, where it just starts spiraling.
Yeah, it starts flying erratically in a spiraling motion, often trying desperately to correct for what it thinks is incorrect heading data because the compass is giving it garbage readings. Very disconcerting to watch and dangerous.
I bet. And this is why compass calibration is important, but it has to be done correctly in the right environment. That seems key.
Absolutely critical. Calibration tells the drone about the magnetic environment it's operating in, specifically to compensate for the drone's own magnetic field created by its electronics and motors. You must perform compass calibration in a clear area, away from metallic structures, vehicles, power lines, rebar, concrete, or any potential sources of magnetic interference.
So find an open field, basically.
Ideally, yes. The source explicitly warns, and this is another crucial point and common exam trick, when should you not recalibrate the compass? Answer: near metal or sources of EMR-Phi. Why? Because calibrating near interference will bake in an incorrect heading or compass bias, essentially confusing the drone with bad data before it even takes off. This can lead to unstable flight or even a flyaway shortly after launch because it thinks north is way off somewhere else.
Okay, so calibrate in the clear, ideally in open field. And when should you do it? After transporting the drone long distances, firmware updates.
Yeah, typically after transport, especially rough transport, after significant firmware updates, after any hard crashes or repairs, or after traveling a significant distance to a new geographic area where the magnetic declination is substantially different, but not near anything metal or emitting fields. And often, you don't need to do it before every single flight if you're flying in a familiar location and nothing's changed. Doing it too often, especially if you can't find a perfectly clean magnetic environment every time, can sometimes introduce more problems than it solves by averaging in noisy data from a less than ideal spot.
Right, don't fix what isn't broken if you're in a known good spot.
Exactly. The source also notes that if you do perform a compass calibration near interference, and that leads to unstable flight or a flyaway that's logged by the drone system, Transport Canada may expect you to document and report the incident under CARS 911.76, which covers reporting certain accidents or incidents. They want to see you understand what went wrong and how you'll prevent it next time, demonstrating your understanding of the system's limitations and best practices.
Okay, so navigation is complex. It relies on this intelligent sensor fusion, has dynamic reliability based on the environment, and absolutely requires continuous pilot monitoring and the manual intervention skills to handle failure scenarios like AT tie mode.
Got it.
That's a lot, just for knowing where you are and staying level.
It is. It's the foundation.
Let's move on to the lifeline, the crucial link between you and the aircraft. The command control link, often just called the C2 link, and the essential fail-safe system.
Right, the C2 link is arguably the single most important safety system because it's your direct connection to the aircraft's status and your ability to influence its actions. It's a crucial two-way communication pathway. You have the uplink, sending your commands from the ground controller or software to the drone, things like stick movements to control flight, camera controls, switching flight modes, initiating autonomous functions.
Telling it what to do.
Exactly. And equally important, you have the downlink, bringing back essential real-time telemetry data from the drone to your ground station. This includes its precise GNSS position, altitude, speed, battery status, motor temperatures, vital system health warnings, and crucially, the status and quality of the C2 signal itself.
And the regulations are very clear on this, aren't they? CARS 901.31 seems central here.
Absolutely. CARS 901.31 is the bedrock requirement. The C2 link must be continuous and reliable throughout all phases of flight, from takeoff right through to landing. This isn't just about being able to control the sticks. The regulation specifically includes the requirement for reliable telemetry downlink.
So you need the info coming back, too.
Yes. The source explicitly says, and this is vital for operational compliance, loss of telemetry alone renders the flight unsafe and non-compliant under CARS 901.31, even if the control link seems to still work. If you don't have reliable information about the drone's health, position, and status, you can't safely be the pilot in command. You're flying blind, essentially.
So if you see that downlink telemetry freezing, stuttering, or dropping out on your screen, even if your stick inputs still seem to work, you have to stop flying.
That's the regulation, clearly stated. If the C2 link becomes unreliable at any point during the operation, meaning either the uplink or downlink, you must discontinue the operation. This is not a suggestion, it's a mandate. It means you can't just keep going hoping it gets better if you see the signal strength dropping critically low, the latency increasing dramatically, or telemetry data glitching out.
Don't push your luck.
Exactly. And importantly, it means if you experience a momentary link loss and the drone initiates failsafe and then you do regain the link, you can't simply resume the mission plan instantly. The source emphasizes you must first verify system stability and safe control before attempting to resume. Make sure everything is actually working right again before you continue.
What about autonomous missions, where the drone is following a pre-programmed path? If the drone is flying itself, do you still need to actively monitor that C2 link? Seems like you could just let it go.
No, absolutely not. 100% yes, you must monitor it. Even during pre-programmed autonomous missions, the C2 link must remain active and continuously monitored by the pilot. You are still the pilot in command, legally responsible for the safe conduct of the flight. If the drone encounters an unexpected issue, maybe unforecasted weather, maybe a system alert, or the mission needs to be aborted for any reason, you must be able to intervene immediately via the C2 link.
You need to be able to take over.
Right. Our sources state unambiguously that walking away from the controller, being distracted, or otherwise not actively monitoring the C2 link status and telemetry violates CON 901.31. That's a serious compliance issue. You have to be supervising the automation.
Latency is also mentioned as a factor affecting the C2 link. What exactly is latency in this context, and why is too much a safety issue?
Latency is basically the delay in the system. Specifically for the C2 link, it's the time it takes for your command, like a stick movement, to travel from your controller, be processed by the drone, and result in a physical response from the aircraft.
Like lag.
Exactly, lag. It's also the time it takes for a change in the drone status, like hitting a waypoint or getting hit by a strong gust of wind, to be sensed by the drone and transmitted back to your ground station display as updated telemetry. High latency means your control inputs feel sluggish and unresponsive. You move the stick, and the drone reacts noticeably later. Critically, it also means the telemetry data you are seeing is outdated. By the time you see the drone's position on your map, it might have already moved significantly.
So you're reacting to old information.
Precisely. If latency prevents safe or precise operation, you must terminate the mission. The sources mention that typical latency targets for safe manual operations are generally considered below 200 milliseconds. Any minor telemetry lag or noticeable delay in control response is not acceptable to ignore in flight, especially if you're close to obstacles or doing precise work.
The sources use an analogy for signal strength called link budget. How does that work? Sounds like accounting.
It kind of is. It's a concept borrowed from radio engineering. Think of it as calculating your total expected signal strength margin throughout the planned flight. It's an accounting of all the factors that affect signal strength: how powerful your transmitter is, the sensitivity of the drone's receiver, the gain and orientation of both antennas, the distance between the drone and the controller, and any expected signal loss along the path due to air absorption, obstructions, or interference.
So planning for how strong the signal should be.
Yes, and ensuring you have enough margin. You need to plan your flight path and operations to maintain an acceptable margin in this link budget, not just flying until the signal warning comes on, but proactively planning to operate well within the system's capability. The analogy is great. Think of signal like money you need to plan a fat budget, a healthy margin, so your C2 link never goes bankrupt mid-mission. Don't operate at the extreme edge of your system's range or capability if you can avoid it. Give yourself some buffer.
What are the common radio frequencies used for C2 links, and what makes them vulnerable?
Most consumer and many prosumer drones use the unlicensed 2.4 GHz and 5.8 GHz frequency bands. These are popular, globally available, but that popularity is also their weakness. They are very crowded and consequently at a higher risk of interference because they are shared bands used by things like Wi-Fi networks, Bluetooth devices, microwave ovens, cordless phones, you name it.
So lots of other things using the same airwaves.
Exactly. Trying to fly in an area with dense Wi-Fi traffic, like downtown or a busy event, can severely impact your C2 link. Specialized professional systems, especially for BVLOS, might use different bands like 900 MHz, which has better penetration through obstacles, or even cellular like LTE or satellite communication systems. But these often introduce different trade-offs, such as potentially higher latency compared to direct RF links or subscription costs.
So what are the specific factors that commonly degrade or cause a complete loss of the C2 link? You mentioned interference, but what else?
There's significant overlap with GNSS interference sources, but also factors specific to radio waves. Physical obstructions are huge. Buildings, dense trees, hills, or even flying inside a structure will block or severely attenuate the radio signal. The source gives a common example. Flying into a shadowed area behind a hill or building causes loss of signal because the ground station loses line of sight with the drone. The signal just can't get through the obstruction. EMI RFI is another major culprit. As mentioned with GNSS, high voltage lines, radar emitters, airport radar, weather radar, crane radar, cell towers, and areas with numerous Wi-Fi routers all generate radio noise that can directly interfere with your C2 frequencies. The source's vivid phrase is memorable. If it has radar or high voltage, give it space or your C2 link will be toast. Pilots must identify these potential sources during pre-flight planning and site surveys and either avoid them or plan mitigation strategies, like flying further away or at different altitudes.
Okay, so obstructions and interference. What about the pilot themselves?
Yes. Critically, the pilot's own behavior and setup can cause problems. Poor antenna orientation is extremely common. Your controller antennas have specific radiation patterns. They aren't like light bulbs emitting equally in all directions. Pointing the tip of the antenna directly at the drone is often the worst orientation for many systems. Typically, you want the sides of the antennas pointing towards the aircraft for the strongest signal lobe.
So know how your antennas work.
Definitely. Your own body can block the signal, especially if the drone is behind you. Operating from inside a vehicle is highly problematic because the car body acts as a Faraday cage, badly degrading C2 signal by shielding the antennas inside. The best practice for a reliable link is to maintain direct visual line of sight with the aircraft whenever possible and fly with proper antenna orientation, ensuring the antennas have a clear, unobstructed path to the drone. Distance, of course, is a factor if you exceed the system's maximum range. And severe atmospheric conditions like heavy rain or fog can slightly absorb the signal, though they are less likely to cause complete failure than obstructions or strong EMI-RFI.
This all builds up to the failsafe system, which is the drone's automatic response, the safety net, when that critical C2 link is lost entirely.
Right. CERN's 901.34 explicitly mandates that the RPAS must be designed or programmed to detect loss of the command and control link and automatically initiate a pre-programmed fail-safe response. This is the drone's last-ditch procedure if it loses communication with you. It's meant to bring the aircraft down safely or return it to a safe location without pilot input.
But this isn't just an automatic default setting you can ignore, right? The pilot has to understand it and program it correctly for each mission.
This is absolutely critical and a frequent area of regulatory scrutiny, especially in incident investigations. The fail-safe behavior you program must be appropriate to the airspace you are flying in and the terrain below. If the default fail-safe setting makes the drone climb to 100 meters, but that climb takes it into controlled airspace where you don't have permission, like Class C or D.
That's a violation.
Big time. Or if it causes it to hit a tall building, antenna tower, or terrain feature because the fail-safe altitude wasn't set high enough to clear everything around, you are legally responsible under CAR's 901.27 Safe Flight Conduct and potentially for any resulting incident or accident. You cannot rely on default settings blindly because they might not be suitable for your specific operating environment. Fail-safe is not magic. It's a contract between you and the airspace you're flying in. Program it carefully, consciously for every flight.
What are the common fail-safe options pilots can typically choose from? What does it usually do?
The most common is return to home, or RTH. Upon C2 loss, the drone flies autonomously back to a pre-recorded home point, usually its takeoff location at a preset altitude, and then often lands automatically or hovers there, waiting for the pilot to potentially take manual control if they regain the link.
And that altitude setting is key.
Absolutely crucial. As we mentioned regarding regulatory responsibility, that RTH altitude must always be set high enough to clear all nearby obstacles and terrain within the RTH path, including things like tall trees, buildings, towers, hills, power lines, everything, and also high enough to avoid entering lower-level controlled airspace without permission. Other options include hover in place, where the drone simply stops and hovers at its current position and altitude. This can be useful in complex environments like indoors, maybe inside a warehouse or under a bridge, where RTH isn't feasible and immediately landing might be unsafe. It gives the pilot time to try and regain the link by moving to a better location. The risks are battery depletion while hovering and, of course, wind drift if it's not in GPS mode.
Right, it could drift into something.
Yeah. Land in place immediately descends and lands at its current location. This requires careful consideration of ground safety. Is it landing on a busy road, in water, into people, or property? Probably not ideal in many situations unless it's an emergency. Advanced professional platforms might offer more granular custom responses, allowing for specific waypoint sequences or other pre-planned behaviors upon C2 loss.
So even though the drone initiates failsafe automatically, the pilot is still solely responsible for how it's configured beforehand. That's the takeaway.
Solely responsible. The source uses a good analogy. Failsafe is your parachute, but you must pack it correctly. The drone will do exactly what you told it through your programming, even if that configuration causes a violation or accident. You need to intimately understand not just that your drone has failsafe, but how your specific model will behave in various failure modes, not just C2 link loss, but also low battery failsafe, loss of GNSS, compass interference, etc. They might all trigger different failsafe logic.
What are the absolute best practices for managing the C2 link and programming using failsafe, both before you even take off and during the flight? What should pilots be doing every time?
Okay, pre-flight planning is paramount. First, program your failsafe response carefully, tailoring the RTH altitude, the home point, and the chosen behavior, RTH, hover, land, specifically for the mission, the terrain, and the airspace you'll be operating in that day. Don't just use a generic default setting from last week's flight somewhere else.
Tailor it every time.
Every time. If your system supports it, test the fail-safe procedure in a safe, open area before flying operationally in complex environments. Make sure it actually does what you expect.
Yeah.
Crucially, perform a thorough check of your C2 link on the ground before taking off. This is often called walking the dog in the RSC community. Power everything on, walk a short distance away with the controller, maybe 50 feet or so, and check that you have a strong, stable signal, immediate telemetry updates, low control latency, and that your antenna orientation is correct.
Like testing the leash before you let the dog off.
Exactly. If the leash isn't solid on the ground, don't trust it in the air. Also, verify that your ground controller's battery is fully charged, as C2 failures often result from ground controller low voltage. The transmitter signal weakens as the battery drains. Do a quick site survey for obvious sources of EMF, like power lines or cell towers nearby. During flight, you must continuously monitor C2 link status, signal strength indicators, latency, and telemetry data displayed on your ground station, even if you are flying an autonomous mission. Make this a habit. Scan these indicators regularly, just like you scan your drone's battery level.
Just stare at the drone.
Right. Look at your controller screen, too. If the link becomes unreliable, signal strength drops critically, or latency spikes significantly, you must discontinue the operation. Don't wait for complete loss. Intervene proactively. If failsafe does trigger unexpectedly, stay calm, observe exactly what the drone is doing based on your pre-programmed settings, and immediately attempt to regain the link by moving to get clear line of sight, adjusting your antennas, or moving away from potential interference sources.
And if you are successful in regaining control after a failsafe event, what then? Just carry on.
No, the source is very clear. If you regain control after failsafe, do a test hover and control input check to confirm full system integrity. You must verify that normal control has returned and all systems are functioning correctly before resuming any mission. If any instability, degraded control, or suspect behavior remains after regaining the link RAND immediately,
Don't risk it.
absolutely not. You cannot simply resume a full flight plan after a C2 link loss event without verifying system stability first. Safety always comes first, mission second. Post-flight, especially for commercial or advanced operations, if a failsafe event occurred, log it in your flight records. Detail the time, location, suspected cause, and the drone's behavior. It's also best practice to log your pre-flight C2 test results and any anomalies observed during flight. Documentation is key.
That's a massive amount of essential monitoring, pre-planning, and pilot skill just for navigation and communications. Wow. Let's move on to how the drone perceives the external environment, particularly other things moving in the sky, and tries to avoid them. Detect and avoid, or DAA.
Right. DAA systems are designed to give the drone a crucial capability, especially as we fly in more complex airspace. Kind of a set of robotic eyes and reflexes, but focused outward on the air environment around it. Their core purpose is to enable the RPAS to autonomously detect potential conflicts with other airspace users or obstacles that might be in its path, and either alert the pilot with sufficient time to react, or in more advanced systems, initiate automated avoidance actions.
And the sources make a very important distinction here, one they call a common exam trick and a frequent point of confusion. DAA is not the same as basic obstacle avoidance that many drones have.
Absolutely correct, and this distinction is critical. Basic onboard obstacle avoidance found on many consumer drones is typically a short-range system. It often relies on forward, backward, or sideways-facing cameras, maybe infrared or sometimes ultrasonic sensors. Its range is usually limited to, say, 0-10 meters, maybe a bit more on high-end models.
Really close-in stuff.
Yeah. Its primary focus is on detecting and avoiding fixed, known objects like walls, trees, or buildings right next to the drone. It's fundamentally a crash prevention system designed to stop you flying into something inadvertently, mostly in VLOS operations.
Well, DAA is aimed at something different.
Yes. DAA is aimed at airspace separation management, operating at longer ranges, potentially hundreds of meters to several kilometers, depending on the technology used. And critically, its main focus, especially for integration into shared airspace, is on detecting and avoiding non-cooperative targets.
Non-cooperative, what does that mean?
It means other aircraft that are not broadcasting their position via a transponder or ADS-B, like some older general aviation planes, gliders, balloons, military aircraft in certain modes, other drones without compatible broadcast systems, or even birds and other flying objects. The source drives the point home with a good line. No obstacle avoidance system ever stopped a Cessna. Obstacle avoidance protects you from hitting a wall right in front of you. DAA aims to protect you from an unexpected aircraft or a flock of birds appearing in the airspace further out.
Okay, that's a clear difference. Obstacle avoidance equals nearby wall streets. DAA equals other things flying in the shared sky, especially things that aren't announcing themselves.
That's the core difference you need to understand for advanced operations and regulations like BVLOS.
Yep.
The concept has interesting origins. There's research into how birds like swallows or even insects manage to fly in dense swarms at high speeds without constantly colliding that informs some visual processing algorithms today. It also drew heavily from manned aviation's traffic collision avoidance system, or TCS.
TCS, right, that's in airliners.
Exactly. It was developed after fatal mid-air collisions in manned aircraft to detect other aircraft equipped with transponders and provide pilots with resolution advisories like climb, climb. TCS relies on cooperative targets broadcasting signals, and it's the direct basis for modern ADS-B technology, Automatic Dependent Surveillance Broadcast, which is now being integrated into DA systems, both manned and unmanned.
And the boom in commercial drones in the last decade or so pushed the miniaturization of this DAA technology, made it smaller and lighter for drones.
Exactly. As the potential for commercial drone applications, particularly BVLOS, became apparent around maybe 2015, 2018, there was a surge in companies focused on shrinking and adapting DAA technologies for smaller RPAS. This led to the development of small, lightweight ADS-B receivers just for drones, compact airborne radar systems, and more sophisticated optical processing using cameras. It's now a significant and rapidly evolving segment within drone technology.
And that fun fact about DAA displays drawing inspiration from radar displays in games like Ace Combat. Is that real?
Apparently so. It's cited as a way to present complex airspace information, multiple potential targets, their vectors, threat levels, in an intuitive, easily scannable visual format that human pilots can react to quickly under pressure. The lesson is, think like a gamer when you scan your DAA display, look for the dots, the vectors, the warnings, scan the whole screen to build situational awareness.
Huh. Okay, what kind of sensors do modern DAA systems typically use? Is it usually one type or a combination?
Almost always a multi-sensor approach because different technologies have different strengths and weaknesses, especially against different types of targets or in different conditions. ADS-B receivers are the most common component. They detect cooperative targets that are broadcasting their position, altitude, and velocity, like most commercial aircraft, and many general aviation aircraft now equipped with ADS-B out. That's the cooperative part, listening for others shouting their location. But to detect non-cooperative targets, aircraft without ADS-B out, military aircraft not broadcasting, gliders, helicopters in certain flight regimes, other drones, birds, you need other sensors. Radar is effective here. Airborne radar on a drone can sweep an area and detect objects based on reflected radio waves.
Like a mini air traffic control radar on the drone.
Sort of, yeah. It's excellent at detecting metallic targets, even against complex backgrounds like bridges or near power lines where optical sensors might struggle with glare or visual clutter. However, radar can be expensive, power-hungry, and may struggle to detect very small, non-metallic targets like small birds or carbon fiber drones at longer ranges. Optic LiDAR cameras are used too, often with powerful onboard processing, to visually identify targets or simply detect movement against the background. Modern algorithms are drawing inspiration from natural vision systems like those insect vision patterns mentioned earlier to detect small, fast-moving objects against complex skies. However, cameras are limited by visibility fog, haze, rain lighting conditions like glare near the sun or darkness, and can get confused by complex visual environments like trying to spot a dark bird against a forest background.
What about sound? Can they listen for planes?
Yes, acoustic sensors use microphones to listen for aircraft engines. They can potentially detect targets even when not in direct line of sight, maybe behind a building, but they are severely limited in noisy urban environments or against quiet targets like gliders or small electric drones. LiDAR is listed as a potential technology, but is less used for DAA today compared to its role in 3D mapping, primarily because it's typically shorter range and often focused downwards or forwards for obstacle avoidance rather than long-range airspace scanning. The overall effectiveness of any DAA system depends heavily on the operational environment. Weather, visibility, and the density of potential targets and obstacles all play a huge role.
How has Transport Canada regulated DAA for RPAS, and is there a big change happening now or in the very near future? This seems like a really active area.
It absolutely is. DAA regulation has been evolving rapidly, reflecting the technology's maturity and the big push for integrating drones safely into the national airspace. Pre-2019, DAA requirements for BVLOS were often vague and custom negotiated on a case-by-case basis for each SFOC application. There wasn't a clear standard.
So it varied a lot.
Right. The 2019 CNCAR's Part 9X regulations mentioned DAA as a potential risk mitigation tool for BVLOS operations, but provided no specific technical standard or performance requirements. This led to some variability in the quality and reliability of DAA systems being proposed in safety cases. You could say you had DAA, but how well did it actually work? Over the last few years, say 2021, 2024, there's been significant pressure from industry and internal review within Transport Canada for more clarity and standardization due to this variability. And now, as of 2025, with the implementation of new regulations like SOR 2025-70, there is a huge shift in the approach for operations requiring DA, particularly BVLS.
Okay, what is that huge shift? What's the big change?
The most significant change is that SOR 2025-70 requires DAA performance must be validated in the proposed operational environment, for which it's being used as a safety mitigation. This is key. It means you cannot rely solely on generic manufacturer claims or lab test data anymore. If you are proposing to use a DAA system as part of your safety case for a BVLOS operation in, say, an urban environment near low-level helicopter traffic,
You have to prove it works there.
exactly.
Yeah.
You must demonstrate validation data for your specific operational environment. You need to show Transport Canada how your DAA system, configured for your drone, performs where you plan to fly, detecting the types of targets expected in that specific airspace under those specific conditions. Generic manufacturer performance numbers are not sufficient. The phrase to remember is DAA proof must match the airspace.
Wow. That's a really significant shift. It puts the onus of proving the DAA system's real-world effectiveness for the specific mission environment squarely on the operator applying for the permit.
Exactly. It's moving towards a performance-based standard rather than just checking a box that says you have a DAA system installed. Future developments will likely include more formal minimum performance standards, maybe specifying detection ranges, reaction times, false positive rates. We might see DAA mandated for more types of advanced VLOS operations, like those operating close to controlled airspace corridors or in very dense urban environments. We'll probably see the development of standardized TC or third-party validation tools and methods. And eventually, a much tighter integration of RPAA DA systems with unmanned traffic management UTM systems and potential interface with traditional air traffic control ATC, making drones a more predictable and cooperative part of the national airspace system.
So with these advanced DAA systems, what are the pilot's responsibilities? Does the drone essentially see everything and avoid it on its own now? Can the pilot just relax?
Absolutely not. This is perhaps the most crucial point in the DAA section, and another common exam trick you need to watch out for. Regardless of how sophisticated the DAA system is or whether it initiates automatic avoidance actions, the PIC, pilot in command, retains full ultimate responsibility for collision avoidance at all times.
The buck still stops with the pilot.
Always. DAA is an aid, not a replacement for the PIC's fundamental separation responsibility.
Wow.
This is a non-negotiable regulatory requirement in Canada today. You are still the captain, even if you have robotic eyes helping you look out.
Okay, the pilot is always in the loop and the final authority. What else does the pilot need to do regarding DAA, especially if it's required for the operation, like in an SFOC?
If DAA is a required mitigation for your operation, such as in a BVLOS SFOC, you have ongoing responsibilities for the system's operational status. This includes performing pre-flight checks of the DAA system's calibration and reported performance status, making sure it's working before you fly, and having a documented maintenance schedule and logs for the DAA components as required under CARS 901.27 for maintenance. You need to ensure the system is functional before and during required flights.
And what happens if the required DAA system fails during a flight where it's mandated, like a BVLOS mission? Can you just continue visually if you have observers?
No, this is critically important, especially under the new regulatory environment. If DAA fails during a required flight, for example, a BVLOS operation where DAA was a specified mitigation in your SFOC, you must immediately execute an emergency contingency action. This typically means a pre-planned procedure such as an automatic RTH or a controlled landing at a designated emergency landing site. Your SFOC must include a specific DAA failure procedure.
So you need a plan B for DAA failure.
Absolutely. And you cannot continue the BVLOS flight with partial DAA failure even if other DAA sensors still seem to be working, or if you have visual observers who are now trying to scan a huge area beyond VLOS. The required safety mitigation is compromised. If DAA is required by SOC, loss of DAA must execute contingency, do not continue BVLOS. You have to bail or land safely according to your plan. The sources provide examples to illustrate this. If your radar, DAA, and BVLSS detects a non-cooperative target threat that the system cannot automatically resolve, your procedure might be for the drone to immediately descend to a safe lower altitude below common air traffic or loiter in a predefined safe zone until the threat passes, or you confirm visual separation through other means. If you're operating VLOS but hear a helicopter approaching and your DAA sensors aren't picking it up or it's ambiguous.
You can't just trust the tech.
Right. You can't rely solely on your obstacle avoidance or even potentially your DAA in that case. You must visually monitor intensely and proactively descend or land immediately if safe to do so. If one sensor in your multi-sensor DAA suite fails while you're BVLOS, even if others are working, you must initiate your contingency, RTH land immediately. You cannot continue the BVLOS mission as the required safety mitigation is no longer fully operational. If you're using DAA voluntarily in BVLOS where it's not strictly required by regulation, it's an advisory tool, but you still must maintain visual separation as your primary method of collision avoidance. You still need to look out the window, so to speak.
Okay, it all consistently comes back to pilot responsibility, understanding the limitations of the technology, and adhering strictly to the operational requirements and contingency plans. And that validation piece, confirming the DAA works for your specific real-world planned flight environment, that's the big regulatory step forward with SOR 2025-70.
Precisely. It's about demonstrating competence not just in operating the sticks, but in managing the complex systems on board and the risks present in the operational environment you choose to fly in.
Okay, so we've covered the brain, FC, the senses, navigation, the lifeline, C2, and seeing the sky, DAA. What about having crucial backup plans in place? Let's talk about RPAS system redundancy.
Redundancy. Yeah, this is a core safety principle in all of aviation, and it's increasingly critical for RPAS, especially as we move towards more complex and higher risk operations. It's simply about having extra components, systems, or even procedures that are not needed for normal operations, but are there specifically to maintain functionality and safety if a primary system fails. Think of them as backup systems or safety margins built into the aircraft's design or your operation itself.
And the goal isn't necessarily to prevent any failure from ever happening, because components can fail, right? The goal is more about managing the failure when it does occur.
That's the core philosophy, exactly. It's often called graceful degradation. If a component or system fails, the RPAS should be designed or operated in a way that allows it to tolerate that failure and remain controllable long enough for you to perform a controlled return to home, loiter safely away from hazards, or land under control at a safe location. The purpose of redundancy is specifically to prevent a catastrophic failure, an uncontrolled crash resulting from a single point of failure in a critical system. It's part of a broader risk management strategy that includes not just hardware redundancy, but also software redundancy, procedural redundancy, and operational checks.
Where do we commonly see redundancy showing up in RPAS design, especially on more professional platforms? What are the key areas?
There are several key areas where redundancy is common or highly desirable. Power systems redundancy is probably the most common you'll see. This often means dual batteries wired in parallel, so if one battery fails or drops voltage unexpectedly, which can happen, especially in cold weather, for example.
Yeah, batteries don't like the cold.
Not at all. So if one pack drops voltage significantly mid-flight with dual batteries, the system can continue drawing power from the healthy battery. The scenario example is exactly that. Losing significant voltage in one pack. With dual batteries, the system continues operating, giving you that crucial margin to manage the situation and get the drone back home safely, rather than it just falling out of the sky immediately. Learning point. Redundancy provides margin to manage failure. It doesn't necessarily eliminate the possibility of any issue, but it prevents the single-point failure crash. Positioning navigation, GNSS redundancy, means having dual independent GNSS receivers, perhaps one receiving GPS and another receiving signals from Galileo or GLONASS. If one receiver experiences interference or partial failure, like getting bad multipath data in an urban canyon, the flight controller can identify the faulty data, deselect that receiver, and continue using the secondary one, allowing for maintained stable positioning.
So it is a backup way to know where it is.
Exactly. The sources note that having only a single GNSS source in BVLOS operations is increasingly seen by regulators as an unacceptable risk because loss of GNSS is so critical for RTH and autonomous flight functions. A simple memory aid here could be Position dual GNSS. Communication links redundancy is absolutely critical, especially in BVLOS operations where visual line of sight cannot be maintained. This might be a primary direct RF link, like using 2.4 or 5.8 gigahertz, plus a backup communication pathway like cellular, LTE, or even satellite communication for very long-range operations. If the primary link is lost due to interference or obstruction in BVLOS, the system automatically switches over to the backup link, allowing the pilot to maintain command and receive telemetry.
Keeps that lifeline connected.
Precisely. Apparently, the first concept of redundant drone comms links was actually developed for spying missions during the Cold War to ensure data recovery, even if the primary link was jammed. A memory aid. Ping redundant comms links.
Okay. And what about the very heart of the system, the flight controller itself, or the sensors it relies on so heavily like the IMU?
Good question. Flight control and sensor systems, IMU redundancy, is found on higher-end platforms designed for critical applications. This means having dual or even triple independent IMUs. If one IMU fails, or perhaps more commonly, if their readings disagree significantly due to vibration or a fault, the flight controller can identify and deselect the faulty unit and continue using the reliable ones through a voting process. Some very advanced systems even have redundant flight controllers working in parallel or a hot standby ready to take over instantly.
Like the space shuttle had multiple computers.
Exactly the same principle. NASA's Pathfinder solar-powered drone back in the 90s famously used triple modular redundancy, or TMR, for its critical flight control computers. If one computer disagreed with the other two, its input was ignored, voted out. Memory aid. Pilot redundant flight controller, IMU.
And the motors themselves, the things that provide the lift, can you have redundancy there?
Yes, absolutely. Propulsion systems redundancy is a key reason multi-rotors, particularly hexagopters with 6 motors, and octocopters with 8 motors, became so popular for commercial work compared to the basic quadcopters with 4 motors. While a quadcopter generally has no motor redundancy, loss of one motor almost always means an uncontrolled crash. A well-designed hexacopter can often land safely with one motor out, and an octocopter can typically tolerate the loss of 1 or even 2 motors depending on the design and how heavily loaded it is.
So more motors equals more safety margin if one fails.
Generally, yes. It gives you a safety margin in case of motor failure or an ESC, the electronic speed controller for that motor, failing. Memory aid. Plain redundant lift systems, even though it's rotors, think lifting capability.
So redundancy isn't necessarily spelled out in a single explicit regulation in CARS Part 9 for all drones, but it's kind of embedded in the expectations, especially for advanced operations or when you apply for an SFOC.
Correct. There's no single section specifically called redundancy requirements in CARS Part 9s that applies universally to every single RPS out there. But the concept is embedded in several places and is a key part of safety management expectations. CARS 901.27 maintenance requires that any redundant systems present on your RPS must be properly maintained, functional, checked during pre-flight procedures, and their status known to the PIC. You need to know if your backups are working.
Makes sense.
CARS 901.33 failsafe implicitly requires consideration of redundancy. Your failsafe logic must account for the presence of redundant systems. For instance, a drone with dual power shouldn't automatically initiate an immediate emergency landing upon detecting a voltage drop on one battery if the other is perfectly healthy. It should probably initiate a controlled RTH or a safe return, using the remaining power wisely. And SFOCs under 901.69 for complex operations like BVLOS or flying over people almost always require specific levels of redundancy beyond the Part 9X baseline, tailored to the specific risks of that operation. That's where it becomes very explicit.
But TP 15263, the knowledge requirements document for the Advanced RPAS pilot certificate, made understanding redundancy concepts explicit for everyone taking that exam now.
Yes, this was a significant shift in the publicly available knowledge requirements. The latest version of TP 15263 explicitly requires advanced pilots to understand redundancy concepts as applied to the major RPAS subsystems: airframe, propulsion, navigation, communication, and flight control. It is now officially fair game on the exam for all advanced RPAS candidates, not just those involved in complex SFOC applications. The expectation has formally moved from being primarily a custom SFOC condition to being a fundamental piece of knowledge required for any pilot seeking an advanced certificate in Canada. Future regulatory amendments are very likely to formalize redundancy requirements further in the CARS themselves, especially for high-risk operations like BVLOS, flying over people, or transporting dangerous goods.
Beyond hardware, you mentioned software and procedural redundancy. What does that entail briefly?
Right. Hardware redundancy is the physical backups, extra batteries, extra IMUs. Software redundancy can include things like watchdog timers.
Yeah.
These are software processes that monitor critical system functions and can automatically restart a process or even the entire flight controller if it hangs or crashes unexpectedly. It's about ensuring the software itself has some resilience to faults.
And procedural. That sounds like things people do.
Exactly. Procedural redundancy is about human and operational backups. This means things like crew redundancy in complex BVLOS operations, maybe having a dedicated visual observer whose only job is scanning the sky, or multiple crew members sharing monitoring tasks so nothing gets missed. It could mean using multiple comm channels or backup communication methods like satellite phones, even if the drone itself doesn't have redundant comms hardware, and rigorous operational checks, especially detailed pre-flight procedures designed to specifically validate the status and function of any redundant systems before you commit to flight.
And the types you mentioned, active versus passive redundancy, what's the difference?
Active redundancy is where multiple redundant systems or components are operating in parallel at all times. They constantly monitor each other's outputs, and if one deviates, the system can immediately identify the failure and switch or vote out the faulty one using the remaining good ones. This is generally superior for critical flight control systems like IMUs or flight computers because the switchover is essentially instantaneous with no interruption. Passive redundancy is where a backup system is present but only engages or is activated if the primary system is detected to have failed. Think of a backup generator that only kicks in when the main power goes out.
Okay. Active is always on, passive waits for failure.
Pretty much. The key concept for both is enabling graceful degradation. The system remains controllable after the failure of one component. If an exam answer or scenario implies an immediate catastrophic crash after the failure of a single component on an advanced or professional system, that is often the wrong choice, as good design should prevent this via redundancy and graceful degradation. Also, be aware that simple software-only monitoring without an independent hardware or procedural backup isn't true redundancy for critical functions, it's just monitoring. Real redundancy needs independent backups. And redundancy is recognized internationally as a key SOAR mitigation strategy. SOAR standing for Specific Operations Risk Assessment, a common framework used globally for evaluating the risk of complex drone operations. Having redundancy helps lower your risk profile.
So for the exam and for real-world advanced operations, what's the critical mindset around redundancy? What should pilots be thinking?
The exam, especially the advanced one, really tests your understanding of risk management. If a scenario involves advanced operations, BVLOS, flying over people, or operating under an SFOC, and it describes a potential single point of failure for a critical system, like only one flight controller, only one GNSS receiver, only one C2 link, that is a red flag. That redundancy should be considered or is likely missing and represents a higher risk. As a pilot, you should always err toward the side of safety and assume advanced systems are designed for or require controlled flight after failure, use of backup systems, and proactive maintenance of redundancy features. Understand the difference in inherent redundancy levels between basic consumer drones, which often have very little, and higher-end enterprise or custom-built professional platforms, which should have more. Master pilots know this distinction intimately and factor it into their risk assessments.
Fascinating. So many layers of backup and validation built into these systems and expected in operations. Okay, let's wrap up our technical deep dive by talking about something absolutely fundamental, going back to basic physics, staying balanced. Payload, center of gravity, CG, and how that affects flight dynamics.
Right, after all this discussion of complex electronics and software, we come back to Newton and the basics of flight. First, just a quick recap of the two main RPAS airframe types we see. Multi-rotor and fixed wing, as they manage lift and balance very differently, which affects how payload and CG impact them.
Multi-rotors are the familiar ones we usually think of as drones, with multiple spinning propellers, right? Like quads, hexes, octos.
Yes, exactly. Quadcopters, hexacopters, octocopters, etc. They achieve both lift and control purely by varying the speed of each individual motor. If they want to go straight up, all motors speed up equally. If they want to roll left, the motors on the right side spin faster and those on the left slow down, tilting the whole aircraft. Their big advantages are vertical takeoff and landing, VTOL, the ability to hover precisely in one spot, and exceptional maneuverability in tight spaces, making them ideal for close inspection work, videography, or operating in confined areas. Their limitations are typically shorter flight times and range compared to fixed wings because hovering takes a lot of energy. As we just discussed, HEX and octocopters offer propulsion redundancy if a motor fails. Their fail-safe options usually involve hold in place, land in place, or an RTH procedure that often ends in a hover or automatic landing. A key operational risk with multirotors, especially new people, is the rotor strike hazard from those fast-spinning blades.
And fixed-wing RPAS are basically like miniature airplanes, wings, maybe a propeller.
Exactly. They generate lift through forward motion using an airfoil shape, the wing, and require a certain airspeed to stay aloft, just like a regular plane. They achieve control using conventional control surfaces, elevators for pitch, nose up down, ailerons for roll banking, and a rudder for yaw, nose left right.
Like a traditional aircraft.
Just smaller. They are far more efficient for covering long distances and extended periods, offering longer endurance and range, making them ideal for large area mapping, surveying, or linear inspections like pipelines or power lines. Their limitations are that they cannot hover and typically require space and infrastructure for takeoff and landing, like a runway, hand launch, catapult, or recovery net. A significant safety advantage is that they can often glide home or to an emergency landing site if power fails entirely, making them inherently more fail-safe for loss of power compared to a multi-rotor which just drops. And they generally have a much lower rotor strike hazard as the propeller is often just at the front or back, not all around. Their fail-safe usually involves returning towards a designated landing area or circling overhead, always requiring forward motion. They often have only a single motor, so typically less propulsion redundancy than a hexocto multi-rotor.
Okay, so the payload is the camera, the sensor package, the cargo, whatever the drone is carrying for the mission. Why is its integration so critical beyond just attaching it securely?
Because of the center of gravity, or CG. The CG is the single theoretical point where the drone's entire mass is considered to be concentrated. It's the point of perfect balance. Its correct placement relative to the drone's design limits and, importantly, relative to the position of the lifting surfaces, the rotors on a multi-rotor or the wings on a fixed wing, is critical for stability and control. Every RPAS model has a specified CG range typically defined by limits forward, aft, left, right, and sometimes vertically. If the CG is too far off from the design sweet spot, flight becomes unstable and unpredictable, potentially even uncontrollable.
What exactly happens to the drone's flight characteristics if the CG isn't within the specified limits? How does it feel to fly?
The impact is significant and depends on which direction the CG is shifted. If the CG is too far forward, so it's nose heavy. On a multi-rotor, it requires the rear motors to constantly work harder just to stay level, resulting in a slightly nose-down attitude required for stable hover, and potentially a subtle forward drift, even when you're not commanding it. On a fixed wing, a forward CG makes the drone hard to climb. Pitch movements feel sluggish or heavy, and results in a poor climb rate. You might need excessive stick-forward pressure just to maintain level flight. If the CG is too far back, making it tail-heavy, on a multi-rotor, it's the opposite. The front motors work harder, resulting in a slightly tail-down attitude and a subtle backward drift. On a fixed wing, this is much more dangerous. Tail-heavy makes the drone highly unstable in pitch, hard to descend safely because it wants to pitch up, requires excessive stick-back pressure to fly level, and significantly increases the risk of stall, especially at lower speeds, because the elevator loses effectiveness or even reverses its effect. The source stresses. Tail-heavy CG is particularly dangerous for fixed-wing aircraft, making flight unstable and highly stall-prone.
So tail-heavy is really bad for planes. What about side-to-side?
If the CG is shifted laterally, maybe left or right, due to a side-mounted payload like some LiDAR scanners, it requires a constant roll input or continuous differential motor speed adjustment on a multi-rotor just to maintain level flight. This is inefficient, increases motor load unevenly, strains the motors on one side, and on some systems might even trigger autopilot warnings or failsafe, thinking there's a control anomaly or a motor problem. An off-axis CG shift causes constant, inefficient control inputs and fights the autopilot. And vertically, does high or low matter? Yes. If the CG is too high, making the drone top-heavy, it becomes prone to tipping or instability in wind during turns or aggressive maneuvers. The source calls this bad U makes drone inherently unstable. Think about trying to balance a tall object versus a low, wide one. If the CG is too low, perhaps due to a very heavy battery mounted underneath, it generally makes the drone more stable in hover, acting like a pendulum, but it can result in sluggish control response and slow pitch roll rates. It might feel less agile.
So even seemingly small shifts in where you put the payload, or using a different battery, can have major consequences for stability and control. What about payloads that aren't rigidly attached, or that move during flight, like a swinging package?
Any moving payload or dynamic CG shift during flight must be specifically engineered and approved to prevent instability. Generally, this is prohibited unless properly engineered, because the changing balance point can very rapidly cause loss of control. Think of the challenge a multi-rotor delivery drone has. If a package is swinging freely underneath it, it becomes incredibly difficult to maintain a stable hover or fly smoothly. The autopilot struggles constantly to compensate for the shifting CG.
And payload mounting itself is a safety requirement. You can't just tape things on.
Definitely not. It's explicitly in the regulations. Payloads must be securely attached to the airframe in accordance with the manufacturer's instructions or established safe practices as per CARS 901.24. Even minor payload movement mid-flight due to inadequate securing can shift the CG enough to cause loss of control, leading to a crash. Payload mounting integrity is a legal requirement for flight safety. Poor mounting or a payload not designed for the drone's vibration characteristics can also induce excessive vibration, sometimes called jello effect in video, which can interfere with sensors like the IMU, damage components over time, or obviously degrade image quality.
And importantly,
all payloads, whether permanently installed or temporarily attached for a specific mission, count toward the aircraft's maximum takeoff weight, MTOW, the overall center of gravity, CG, and the aircraft's flight characteristics under CARS. You must ensure that with the payload installed, you are still within the manufacturer's stated MTOW and CG limits, and that the drone still performs safely, it can still climb well, hover stably, etc.
how has the regulatory framework evolved regarding payload and CG management in Canada? Has it gotten stricter?
Like other systems we've discussed, there's been a major shift in how Transport Canada addresses this, moving from relying largely on custom SFOC conditions before the 2019 SCARS update to explicit requirements within CARS Part 9, SR 2019-11, that apply more broadly. The key CARS sections pilots need to know are 901.23 operating limitations. This states you must operate the RPAS within its stated operating limitations, including weight and balance, which includes CG. If your payload causes the drone's total weight to exceed MTOW or the CG to go out of the published range, you cannot legally fly that aircraft in that configuration, even if you are an advanced pilot. It's a hard limit. 901.24 configuration. This prohibits modifying the RPAS or installing payloads unless done according to the manufacturer's instructions or documented best practices. It specifically requires that payloads are securely attached and do not interfere with the safe operation or cause instability. Payload mounting integrity is a legal requirement directly tied to the CAR 901.27 perform. This requires the RPAS to have sufficient performance to conduct the intended operation safely in its intended configuration, including with the full payload installed. This means verifying you still have adequate climb rate, hover power margin, enough power left to maneuver or fight wind, and predictable control response with the payload installed. It can't be struggling just to stay airborne. The post-2019 regulatory approach has put increased emphasis on the pilot's responsibility to perform CG weight checks before every flight, not just once when you first get the drone or the payload. Every time you change the configuration, you need to check. The prohibition on dynamic CG shifts, unless specifically engineered and approved, is clearer. More documentation is generally required for weight and balance calculations and checks for advanced and BVLOS operations. And significantly, there's increased scrutiny and more scenario-based questions on payload and CG management appearing on the Advanced RPAS exam, TP 15263, by 2024-2025. Future expectations likely include requirements for electronic documentation of weight and balance for commercial ops and a deeper understanding among pilots of how payload affects autopilot performance and stability algorithms.
So what are the absolute best operational practices for a pilot regarding payload and CG, both before and during flight? What's the checklist?
Okay, the fundamental checks before every single flight. 1. Never exceed the manufacturer's published maximum takeoff weight, MTOW, with the payload, batteries, and any accessories installed. Use a reliable scale if necessary, don't guess. 2. Ensure the center of gravity, CG, is within the manufacturer's published limits. These are often marked on the drone itself, or clearly defined in the manual, with the payload installed in its operational position. Balance the drone physically if possible, or use calculation tools if provided or available. Remember, improper CG, illegal to fly. 2. Ensure the center of gravity CG is within the manufacturer's published limits. These are often marked on the drone itself or clearly defined in the manual, with the payload installed in its operational position. Balance the drone physically if possible, or use calculation tools if provided or available. Remember, 3. Ensure the payload is properly and securely fastened using appropriate mounts and will not shift, vibrate excessively, or interfere with propellers, sensors, landing gear, or any moving parts during flight. 2. Ensure the center of gravity, CG, is within the manufacturer's published limits. These are often marked on the drone itself or clearly defined in the manual, with the payload installed in its operational position. Balance the drone physically if possible, or use calculation tools if provided or available. Remember. 4. Mentally or ideally, through a brief test hover, verify that the drone still has sufficient performance with the payload. Does it have adequate hover authority? Isn't struggling at 80% throttle just to hover? Does it climb reasonably well? And are the control responses stable and predictable? Then, during flight, especially right after takeoff with a new or changed payload, if you start flying and notice instability, perhaps unexpected drifting and hover, unusually sensitive or sluggish pitch roll response, difficulty flying a straight line, or strange oscillations, land immediately. Don't try to fight it or compensate with the sticks or change flight controller settings in the air. That instability is almost certainly a direct result of the balance being off or the payload shifting. Land the aircraft safely as soon as possible.
And after landing, if that happens.
Figure out what went wrong before you try again. Verify CG and balance before the next flight. Double-check the payload mounting. Did something slip? Do not fly again if weight is over MTOW or CG is outside published limits. For custom payloads or configurations not specifically covered in the drone's manual, best professional practice dictates conducting documented test flights first in a safe, open area to carefully evaluate performance and stability before flying operationally near anything important. Logging your calculated CG offset for different standard payloads can also be valuable professional practice for consistency. And understand how that extra weight or changed balance affects things like the autopilot's tuning. It might oscillate if the gains aren't right for the new weight, the RTH altitude needed because climb performance might be reduced, and glide performance for fixed wing. It changes everything.
That brings us to our key takeaways. We've covered a lot of ground on these critical onboard systems and the pilot's responsibility related to them. It seems like there's a lot more going on than just flying.
Absolutely. It's about managing the whole system. To quickly reiterate the most critical points that are essential for safe advanced operations and understanding the current regulatory landscape. First, DAA is fundamentally different from basic obstacle avoidance. Its purpose is airspace separation, detecting non-cooperative targets like other aircraft and birds, often at longer ranges. Know the difference. Second, as of 2025, SOR 2025-70, for operations where DAA is required as a safety mitigation, its performance must be validated for your specific operational environment. Generic manufacturer specs aren't enough anymore. Proof has to match the airspace. Third, the pilot in command, PIC, is always ultimately responsible for collision avoidance, regardless of the presence or actions of DAA or other automation. DAA is an aid, not a replacement for your responsibility. Fourth, if a required safety system like DAA fails during an operation where it is mandated, like BVLOS, you must immediately execute your pre-planned emergency contingency, typically RTH or landing. You cannot simply continue the flight. DAA fail is bail or land. Fifth, on the navigation side, remember GNSS, GPS quality is dynamic and environmental. You must monitor satellite count and HGO-PPP DOP in flight. Just having a GNSS lock before takeoff does not guarantee good positioning throughout the mission. Be ready to handle ATA mode. Sixth, return to home, RTH, depends on reliable GNSS and requires careful pilot configuration of the RTH altitude to be high enough to clear all potential obstacles and terrain along the return path and avoid violating airspace. You, the pilot, are legally responsible for setting this correctly. Seventh, the command and control C2 link must be continuously reliable. This includes both the uplink commands and the downlink telemetry. Loss of reliable telemetry alone makes the flight non-compliant and requires you to discontinue the operation. Monitor signal strength and latency constantly. Eighth, your own pilot behavior, like antenna orientation and operating location, not inside a car, significantly impacts C2 quality. Maintain line of sight and use proper antenna technique. Ninth, redundancy is a key safety principle for advanced operations, enabling graceful degradation instead of catastrophic failure upon a single component failure. Understanding redundancy concepts across different subsystems, Power, position, pilot FC, ping comms, plane propulsion is now an explicit knowledge requirement in TP 15263 for advanced pilots. And finally, 10th, payload and center of gravity CG management are fundamental pilot responsibilities explicitly covered in CCARS 901.23 and 901.24. Improper CG leads to unstable, unsafe, and illegal flight. You must check your weight in CG before every flight with the payload attached, and if you observe instability after a payload change, land immediately and verify the balance.
Wow, that's a comprehensive list. Mastering these systems, really understanding their capabilities and their inherent limitations, coupling that technical knowledge with diligent pre-flight planning, continuous in-flight monitoring, and practicing those crucial manual intervention skills for when things go wrong. That is what truly makes a safe, competent, and professional RPAS operator. It goes far, far beyond just being able to control the sticks well. It's about being a system manager and a risk manager in the air.
Couldn't have said it better myself. And thinking about these interconnected systems, how they work together to provide layers of safety, and critically, where those layers can potentially break down, leads us to maybe a provocative thought as the technology continues to advance so rapidly.
What thought is that? Where is this heading?
Well, as drones become increasingly autonomous with systems like highly sophisticated DAA, potentially capable of detecting and deciding on avoidance maneuvers almost instantly, and as they become more integrated into complex national airspace structures like unmanned traffic management, UTM systems, maybe even interacting directly with air traffic control in the future, how does the fundamental role of the human pilot change?
Good question.
If the systems are designed to do more and more of the routine seeing and deciding in normal operations, potentially with less frequent need for manual stick input intervention, what then becomes the pilot's ultimate, most critical responsibility in this increasingly automated future? What specific skills, perhaps related more to high-level system monitoring, oversight, anomaly detection, complex troubleshooting, and maybe decisive intervention in rare but potentially more complex cascading failure scenarios will be paramount then? What does it mean to be in command when the machine does most of the flying?
That's something significant to consider as the lines between pilot and system manager continue to blur and evolve. What skills do we need for that future?
Indeed it is. The technology is moving forward incredibly fast, and the demands on the pilot are evolving right along with it, focusing more and more on understanding the machine from the inside out, managing the automation, and being ready for the unexpected.
That's been a really deep dive into the hidden systems that make safe drone flight possible. We hope this gave you some valuable insights and clarified some key concepts for your operations and perhaps your studies. Thanks for joining us.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.